Welcome to Math 106, chapter 4.3, where we talk a little bit more about differentiating our exponential functions. And we're going to be using more specifically the chain rule, and then we're going to get familiar with that. So far we know that the derivative of e to the x is itself. That is what we learned from your previous section. Now we can apply the chain rule if we understand composite functions. Now keep in mind your composite function back from chapter 0. And again, when we first learned that chain rule back in chapter 3, we said, hey, a composite function is comprised of two different things, right? So in our case, if we were taking a look at something like e of g or e to the gx, right? That g to the x is going to be that inside function. And if we got rid of it, right, whatever is left over is your f of x. So pairing that with your chain rule, right, if we're doing the derivative of e to some exponent, right, well, we derive your outside function first, right? So take the derivative of the outside, that being e to the gx, keeping the gx the exact same, and then you can derive your inside function, that is the exponent. So this is the derivative of the exponent. That being right here. And then this one, right, this f prime, that is your f prime here. So derivative e, we'll just say g to the x, which is just e to the gx. So if we were to put the chain rule all together, right, using e to the gx, we're just going to say, okay, well, we first derive your outside function. That is just itself, keeping everything else the exact same. This is f prime of g of x. Now we get to derive g of x. So now it's g prime of x. This is the derivative of your exponent. And it could be anything. You could also use as we've seen before in chapter 3.2, where we learned about your chain rule, that we could have it in a different terminology. We could say this is really e to the u, where u is g of x. And then, of course, you have to derive in those certain aspects. So let's take a look at example 1. Actually, let's take a look at, we'll do example. Actually, we're going to go over to this worksheet and do just a couple quick ones. Just to start us off, let's just do 33, 34, 36. So just those few, and then maybe we'll go down to 41 and expand a little bit more. All right, so with your chain rule here, right? Chain rule we said was f prime of g of x times g prime of x. And so your exponent, right, your x value, or f of x, I should say, is e to the x. And when you derive it, right, it's just itself. Whereas g of x is going to be your exponent, 2x. And so your derivative of 2x is just 2. So when you complete your chain rule all together, right, it should look something like this, right, where you have the derivative of f. So that is over here. And instead of just saying x, we have to put g of x on the inside, right? That is your exponent. And then you can multiply it by g prime of x. That is just the value of 2. So what that looks like as your chain rule, we say e to the 2x times 2. That is your derivative down here. So that being said, right, we have this portion here. Your g is here. And your g prime is that one. So all together we have 2e to the 2x. So if we were to try it again, right, If you still need to break it up into parts, I'll do it one more time. So it's just e to the x. That is the main function, right? That is the outside function. And the derivative is just itself. G is your exponent, negative 8x, and g prime of x is going to be just negative 8. So the chain rule, right, as we've done before, is just saying, okay, let's take your derivative of f, and on the inside in your exponent, that is going to be your g of x times the derivative of g. So it kind of does this like little kind of zigzag motion, right? So if we put it all together, we have e to the negative 8x times negative 8. And I want to make sure I highlight the exact same. So we have the derivative here of f. We have g on the inside, and then we have your negative 8 from the outside. So altogether, we have negative 8 e to the negative 8x. Or if you want, because you have a negative exponent, we can keep a negative 8 above because that one is not does not have a negative exponent. Instead, we can drop this one down. So let's have you try number 36. So the chain rule, right? We have e to the negative 2x cubed. So it's the derivative of itself times now the derivative of this one, right? Negative 2 times 3, that makes negative 6x squared. So altogether, we should have negative 6x squared times e to the negative 2x cubed. And if you want, we could also adjust that a little bit to make it a positive exponent. And there you go. Now, when you're ready, let's try 41 here. Our primary rule, as we can see it, is your product rule. Product rule says that we are just going to take the time to derive each one separately and put it all together. So f of x is going to be your first one. That is just x cubed. So f prime of x is going to be 3x squared. G of x is just e to the x, and g prime of x is again itself. So that product rule, right, it just says that we're going to take the derivative of f, so that is 3x squared, times e to the x, plus your f of x, that was x cubed, times the derivative of g, that is e to the x. And now, if we can bring things out, notice that we have an e to the x, so we can pull that one out. We also have 3 x's here and 2 x's here, so we can take out 2 of those x's, leaving behind 3 plus x. And that would be your final final notation. And I'm just going to spend a moment highlighting for a second. Here we go. Here we go. Here you go. And when you're ready, why don't we try one more? Let's do 42. Let's do 42. So we have f of x is equal to x squared. F prime of x is equal to 2x. G of x, we have e to the negative x. G prime of x, right? This is where your chain rule comes in. It's itself, right? Itself first, times now the derivative of negative x. That would just be a negative 1. So we have negative e to the negative x altogether. So now let's go ahead and do your product rule where we have negative, we have f prime of x, g of x, plus f of x times g prime of x. So when we put it all together, we should get 2x e to the negative x plus f prime, or f of x, that was just x squared, times g prime. That would be times this negative e to the negative x. Now, if we were to take things out, notice that we have an e to the x, or an e to the negative x, so we'll take that one out. We also have two x's here and one x here, so we're only going to take out one of those x's, leaving behind a 2. We did not, so notice that if these both go away, you're left with the 2. Plus, we have that negative, so now we have a negative sign. And we took all from here, and you still have one of those x's, so it's minus x. And there you have it. And again, I'm just going to spend a moment highlighting, just so you can kind of trace where they come from. Oops, I highlighted the wrong ones, didn't I? And one more. All right, so now let's go back over to your guided notes and have you try just 2 or 3 more. And then we're going to kick up the differential a little bit further with example 2. So here is just like that chain rule, getting some practice with it. So if you still need to break it up, oops, that's fine. It's just itself. G of x is your exponent, and g prime of x is 5. So when we put it all together, keep in mind we have the derivative of the outside, keep the inside the same. So that would be e to the 5x, that is itself, times now the derivative of g to the x, that would be, or sorry, g of x, that would just be your 5 here. So again, we're left with 5e to the 5x. So kind of retracing your steps, right? We have your g here, your f on the outside, that is just this one. And you have this one over here. Let's do it again. And this one, I'm not going to kind of break it up with the chain rule. I'm just going to go right for it. So first, we have the derivative of e itself. That would be e. Now we get to keep everything the same, so your exponent stays the same. And now we can derive your exponent, so that we would get 2x. So altogether, we should have 2x e to the x squared minus 1. Now this one, right, if we were to first do the chain rule, right, we take the derivative of e, that is itself. And now when we go to derive, right, we are going to multiply by the derivative of this one. We might want to use that quotient rule. We have f prime of x, g of x minus f of x, g prime of x over g of x all squared, right? Or high d low, low d high over low squared, right? Where if we say, okay, f of x, that is x minus 1. Therefore, f prime of x is 1. G of x is just x, and g prime of x, again, is just 1. So if we were to put it all together, right, we have 1 times x minus 1 times 1 all over x squared. So we have x minus x plus 1. So these will end up canceling. So we're left with 1 over x squared. This is the derivative of g of x. If this is g of x, g prime of x is now 1 over x squared. So altogether, we have 1 over x squared e to the x minus 1 over x. Or your alternate solution, if these are being multiplied, right, this is kind of over 1. Therefore, we can put x squared down below. So let's have you try it one more time with example 2, kind of kicking it up that notch. So see what you can do just by pausing the video. Well, f of x, right, is 3e to the 2x. And when we take the derivative of it, right, with your chain rule, right, keep everything the exact same to start, and now derive your exponent. That would just be 2. So we get 6e to the 2x. That is the derivative of f of x. So now g of x, we have 1 plus x squared, and its derivative, x. Now we're going to be recalling your quotient rule. Quotient rule, we're just taking the derivative of the first, leaving that one alone, taking turns once more all over g of x squared. So the derivative of f of x, that would be this one, is 6e to the 2x times g of x, that is 1 plus x squared, minus f of x, we have 3e to the 2x times the derivative of g of x, all over 1 plus x squared, all squared. And I'm just going to spend just a second highlighting. Oh, I missed one. There we go. So now let's see if we can clean it up just ever so slightly. You'll notice that we have a 6, and actually if we were to clean it up all the way, right? 6e to the 2x, 1 plus x squared, minus 6x, that is coming from 3 times 2. The 3 came from your f of x. The 2 came from the derivative of g of x. And note the 1x squared squares, these do not cancel because this one does not have the ability to cancel them all out. So instead, right, notice that they have a 6 in common. So we can take out the 6. We can also take out the e to the 2x. So in its place, we took out the 6, e to the 2x. And so notice that this one didn't get highlighted, so that one gets to remain behind. And this one, we just have an x that did not get highlighted, so we have minus x over here, all over 1 plus x squared squared. Let me rearrange that ever so slightly and kind of keep track of what got highlighted, how that came out. And then we can always check if we do have those 3 terms, see if we can factor. But keep in mind, factors of 1 is just 1 and 1, and there's no way to arrange it to get that middle term of a negative x, so it is not factorable. So therefore, we are finished with simplification. And there you have it. So now let's move on to example 3, where it says an investor puts $25,000 in 2 separate stocks, A and B. They invested $15,000 in A and $10,000 in B. The value of their accounts in thousands of dollars, T years from inception, is given by the formula, and they give us a function here. Then it says, what is the value of the account after 4 years and then after 12 years? So for us, right, keep in mind, we have 2 different accounts where we invested 2 separate values. And that is what they have done for us here, is that they're telling us, okay, well, we have their accounts in thousands of dollars. So what they have done is they have taken this 25,000, they split it up into 15,000. So that's where this 15 is coming from, and 10,000. And that's where this 10 is coming from, because it's implied that it's in thousands of dollars. Now they also have different sort of rates to them. So you'll see that here. And so they've given us this function after telling us this whole thing. So now we want to know, okay, of your function, how much is in the account after 4 years and again after 12 years? So this is just your t is 4 and t is 12. So we can say, okay, with this $15,000, e to the 0.02, that was your rate, over 4, plus 10 e to the 0.06 to the 4. And one more time with 12. And we want to know approximately how much is here. So I'm going to pop over into Desmos and see what we have. So Desmos Scientific, I think I have lots of, let's see if I can clear them all out. There we go. So initially we have 15, and when you want to do E, we're just going to go over to your ABCs and click E. And you'll notice that it's starting to formulate that up there. We're going to raise it to 0.04, I believe. Nope, 02 times 4. Back up, there we go. Times 4 plus 10 e raised to the negative 0.06 times 4. And there you have it. So we have 24.11558. So we're going to put that in here. We said 24.115.58 or so. And notice that I actually moved things around. Right, that was your answer here. But keep in mind, this is in thousands of dollars. So we get to move this over 3 times to imply the thousands. So we have $24,115.58 in your account after the 4 years. And if we were to do it again with your 12, all we have to do is swap the 4, there we go, for a 12, and one more time for a 12. So now we have 23.936258 or so. So we are going to, one more time, put that into thousands. So hopefully I can remember my values, 239,36259. I already forgot. 259. So one more time, let's move it over 3 decimal places. So we have 23,936 and about 26 cents in your account after 12 years. So then it's going to ask, okay, well, at what rate, right? And we're talking, we talked about in chapter 3, what we do when we see the word rate. Rate means that we're going to do what? Well, this is the derivative. We want to know how fast is it changing in the account after the 4 years and again after the 12 years. So first we need to come up with some sort of derivative for this function. We have f of t is equal to 15 e to the 0.02t plus 10 e to the negative 0.06t. So if we're asked to derive, right, let's just take it in chunks. So first derive this chunk. So you have 15, and the derivative of e, right, is just itself. So we keep everything the exact same. And then we do your chain rule where we then get to derive your t. So if we wanted to multiply, right, 15 and 0.2, we'd get 0.3, at least I believe so. 15 times 0.02. Yep, 30. 3. E to the 0.02t. So that is the derivative of your first. And then we'll add it, or, well, premature. So let's take the derivative of the second. So we have 10. Derivative of e is just itself. So writing the exact same thing. And now let's derive t. So the derivative of t is negative 0.06. So now we need to multiply 10 and 0.06. So that would make it negative 0.6 e to the negative 6.06 t. So this is the derivative altogether of f of t. So now we want to know, hey, given that this is now your derivative, let's figure out, okay, at what rate is the account changing after the 4 years and after the 12 years? So if we have your derivative here, we now know, okay, we're going to focus on the year at 12 or at 4 and then again at 12. So we're going to just take the derivative and now punch in your value. And you'll notice I'm leaving a gap. That's because I'm just going to copy and paste. Again for 12. And let's go ahead and punch that value in. So we have 0.3 e to the 0.02 times 4. So that was 1 minus 0.6. I believe it was 0.6. Yep. E to the negative 0.06 times, oops. I like using parentheses, negative 0.06 times 4 parentheses. And let me just verify that I've typed that in correctly. Okay, so I'm going to round to 2 decimal places. So we have negative 15 or 0.15. We're going to do it again with 12 here. And 0.09 or so. So this is roughly negative 0.15. This is roughly 0.09. So what does that mean? Well, it means that we are decreasing in your account after that 4 years of about $1,500 per year, or in our case, it could be $15,000 per year. Oops. Or in this one is increasing because it's positive. And again, if you didn't want to say, okay, thousands of dollars, you could also move your decimal places over 3, and then you would come up with your value. So this would be, right, 150, or this one would be 90, right? So $90 per year, $150 per year, and so forth. Now let's get to our very last example, example 4. It says, write the equation of the tangent line. Notice that we have come up with that one a lot, and now we're going to compound it with, okay, now let's derive your e with the chain rule. So through the point of 0 and 5. So see if you can pause the video and try this one out. Well, first, if we're talking about the tangent line, I need the derivative. So if this is your y, I'm just going to write it down real quick over here. So if we're taking the derivative of y, right, keep everything the exact same. Using your chain rule, we can now derive your x plus 2. So this is on our way to get your slope. And now we want to know, okay, this is your slope. And now we want to know, okay, this is when x is equal to 0. So given that x is equal to 0, we're going to go ahead and plug it in. 5e to the 2 times 0, oops, times nope, times 2. So that would make 10, but I'll just keep it the same. So we have 10 e to the 0 plus 2. E to the 0, right? Anything to the 0 power is 1. So 10 plus 2, that would make 12. So your slope here is 12. So far, right, if we're looking at y equals mx plus b, we have your slope of 12. We have the point 0 and 5. This is when x is 0 and y is equal to 5. This is your y-intercept. Anytime they give you an x value of 0 and your y value, that is going to be your y-intercept. So we could actually put this all together. Y is equal to 12x plus 5. Your y-intercept is equal to b. And there you have it. So hopefully that makes sense on how we use your chain rule. If you want, you can try out a few extra of these. You might not know the derivative of ln yet, so you can keep those kind of for later. Otherwise, I'm sure you can derive the remaining few.